Hello everyone. We've been looking at supervised learning. Specifically, we started looking at the problem of regression, and we posed it as a problem of linear regression, where we wanted to search for linear functions that best fits the data in the sense of squared error. We looked at the fact that linear regression can be solved in analytical form. That is, you have a closed form solution in the sense that W star can be written exactly as a function of x and y. And then we looked at we asked some questions about the nature of solution and what more can we understand about linear regression. Towards that, we have already looked at the geometric view of what it means to say W star is of a particular form, specifically XX transpose pseudo inverse XY. What does it mean by that? We have looked at the geometric interpretation. So now in this video, what we want to do is look at few more questions about linear regression and then try to address them. The first question that we will consider today is about the computational considerations with respect to linear regression. Computational considerations. So one thing that is good about linear regression is that we have a closed form solution for this for the optimal W, which is of the form x transpose pseudo inverse xy, right? Now it's a great thing that we can solve this as just an equation, right? So given data, I can just compute x transpose pseudo inverse xy, and then I get my W star, which I later use to make my predictions on test data. However, the issue is the issue that might crop up is how computationally expensive is it to compute this W star. Now, if you take a look at the form of this W star, the main culprit here at least seems to be immediately this inverse or pseudo inverse, right? So, in general, you can assume this is an inverse also, that's fine. So, this inverse computation is expensive if D is large. Remember, we made a similar comment when we were doing PCA that you wanted to compute the eigenvectors of a covariance matrix, and we said that the eigenvector computation is typically hard, not hard, so it's computationally expensive of the order D cube. The inverse computation is exactly as hard as doing the eigenvector computation, because if you know the eigenvectors, you can actually compute the inverse very easily by just inverting the eigenvalues and so on, right? So the question is, what time does it take? So this also takes something like order of D cube. Maybe there are more specific special purpose algorithms which can do it slightly faster than this, but then in general this is also going to take D cube, where D is the number of features, right? So remember, XX transpose is of the form is D cross D matrix. Okay, so now the question is, if we cannot do this inverse, then how can we solve this problem, right? So we know that this is the solution, yet we cannot compute it because D is large. Maybe D is billion, right? So you have billion features, so you cannot invert that easily, a billion cross billion matrix. It's going to take too much computational effort. So the question is there a different way to achieve the same W star without computing the inverse, right? So this is a very practical question that one must ask, because at the end of the day, it's not just the theoretical part that one needs to understand. Of course, the theory builds the foundation, but then what challenges might arise when you actually implement it in practice is also something to keep in mind. Okay, now without computing the inverse, can we do something? Well, we know that W star is the solution of an unconstrained optimization problem, right? So remember, W star is just the minimizer of the sum of the squared errors, or the average of the squared errors of the prediction W transpose xi minus yi, right? So now, because this is W star can be any vector in D dimension, and it's a solution of an unconstrained optimization problem. Now we can use general purpose tools to solve unconstrained optimization problems to solve for W star also. And one of the most popular tools, general purpose tools to get W star or in general to get the minimizer of a function is the method of gradient descent. Well, a very quick primer of what gradient descent is in case you are not aware of it. Gradient descent is an iterative way to find minimizers of functions using just first order information. When I say first order information, it is the first derivative, or in higher dimension function, it is the gradient, which is just a vector of partial derivatives. So, what is the gradient descent algorithm, right? So, you start at some point, some guess for your solution, which let us call that guess as W naught, which is some arbitrary point in d dimension, and then you compute the gradient of the objective function at the point W naught where you are, right. So, the gradient would tell you the direction in which you have to move such that the function increases the most, right. So, the direction where the function gives the highest increase is what is given by your gradient. Now, we want to minimize the function. So, naturally gradient descent would tell you, well, move in the direction opposite to what the gradient is pointing, right. So, the gradient would tell you which direction you have to climb the mountain. The negative of the gradient would tell you the direction in which you have to move so that you reach the bottom of the mountain, right. So, you kind of reduce your function value. So, the update rule would be Wt plus 1 would be Wt minus the gradient of the function, any general function evaluated at Wt, but then you do not take a full step necessarily in the negative gradient direction. The minus says that you are moving in the negative gradient direction. This is the gradient at Wt, but then you move some scalar times the negative gradient, where scalar tells you how much step should I take in the direction of pointed by the negative gradient. So, this is the step size basically. Now, the property of this algorithm is that if you choose the step size carefully, then if you keep repeating this process, this is an iterative algorithm, you take a small step in the gradient direction, at that new point the gradient of the function might point you in a different direction, and you keep doing this, eventually you will reach what is called as a local minima of the function. Now, a local minima is a point where the gradient becomes 0, and it does not mean that it is necessarily the global minima. For example, you might have a function like this, where this is a local minima, this is a local minima, whereas this is the global minima of this function, which means if we start at this point, then if you start at this point, then you will move in this direction and you will reach this point, which is a local minima, and then your algorithm does not proceed any further. It kind of stops at that point because the gradient becomes 0, and then this update rule does not proceed any further. However, if your function is nice, not wiggly like this, but then if the function is nice, something like this, then yes, your gradient descent algorithm, in fact, does not matter where you start, will converge to the global minima, because there is only one global minima, or every local minima is also a global minima. And it turns out that for the function that we care about, which is the sum of the squared errors, is in fact a function that looks like which does not have wiggles, right. So, it is a quadratic function in W, and quadratic functions are a subset of a class of functions called convex functions, which have a unique global minima in this case, right. So, which means you are for which all local minimas are global minima, which means that your gradient descent algorithm will in fact converge to the optimal point, right. So, we can apply this. Yes, this is an alternate way to solve the same problem. The question is, does it solve our original problem, which is like we had a problem of computing inverses. Now we are saying, well, I do not care about one shot solution, right. So, I do not need an equation, but then I will do it in an iterative fashion, but then my inverse computation should go away. Now, the question is it going away in this particular example? Let us see that. You may want to pause and think about this, and I will tell you what the solution is at this point. Okay. So, what is the function that we care about, right? So, our function is f of w is simply norm of x w minus y squared, right, which is simply sum over I equals 1 to n w transpose x I minus y I squared. We saw this already, that these two things are the same. Now, for this function, one can compute the gradient, and the gradient would look something like 2 times x transpose w minus 2 times x into y. Now, this is a simple exercise, please verify this for yourselves. You just have to take the derivative of this function with respect to each component of w, and then get a vector of partial derivatives, and that would give you exactly this, right. So, it is a good exercise to verify this. If you are not that comfortable with partial derivatives and so on, it is a good exercise to try this right. So, which means what does this tell us? This tells us that gradient descent update rule for our linear regression is going to look like this. Wt plus 1 is going to be Wt minus some constant scalar eta t times 2 times x transpose w minus 2 times xy. This 2 is not so important. You might have added a half in the original function, and I could have thought of this f of w itself as half, and then the 2 would cancel out. That's usual practice, but then here I am not doing that, but it wouldn't really matter. The 2 can be absorbed in the constant, if you will, the step size, I mean. Okay, so the good thing here is that there is no inverse computation happening here. As you can see, Wt plus 1 is Wt, the current W, minus some scalar times some quantity which does not require the inverse to be computed. So, we are not computing the inverse at all, yet we will converge to W star, which would have essentially computed the inverse and then done an x transpose inverse xy, right. So, we are mimicking that, not in one step, in multiple steps via the gradient rule, but eventually you will converge to the same W star, which is a good thing, right. So, computationally we are never computing the inverse, right. So, even if d is much large, even if d is in millions, number of features that you have is in millions, you can still run this algorithm. That is what this kind of tells us, if your inverse computation is a bottleneck. Now, what might also happen on the other hand is, one might ask the question, well, if d is large, we have a problem. We have kind of solved that by going to this gradient descent algorithm. What if n is large, right? So, the next question is, what if n is large? Well, n is the number of data points, right. So, let us say hundreds of millions, right. So, now what is there an issue that that we want to solve here? Well, now remember, gradient descent is an iterative process, right. So, at every round you need to compute the gradient, right. So, which means that you need to compute, the gradient requires x transpose to be computed, and x transpose is a d cross d matrix, but then it came from d cross n times n cross d matrix. So, there is an n dependency hiding inside this x transpose itself, and if n itself is in billions, then even computing this x transpose might actually be a hard thing to do, right. So, we may want to might want to avoid x transpose computation itself, not just the inverse of it, but even x transpose might be hard to compute if you have huge number of data points. So, now the question is, well, then it appears that we cannot even run gradient descent because it needs x transpose, and that might be computationally expensive also. The question then we ask is, how to adapt gradient descent to this situation, right. Can we somehow mimic something like gradient descent to get rid of this problem of computing x transpose? Well, the surprising answer to this is yes, you can get rid of this, both the D problem and the N problem. The D problem via using a gradient descent algorithm, the N problem via doing some variant of the gradient descent algorithm, which is a very popular algorithm that people use in practice all the time. And let us look at what this variant is. This variant is what is called as stochastic gradient descent. It is a variant of gradient descent. There are several variants. I am going to give you one simple variant of gradient descent here. Like gradient descent, it is an iterative algorithm for t equals 1 dot 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 some capital T. You can have a fixed number of rounds that you want to run this algorithm for, or you might have some convergence criteria that is similar to what gradient descent would do. Nevertheless, let us say we have a budget number of rounds for which we want to run this algorithm for. Now, what you do in stochastic gradient descent differently from gradient descent is that the first thing you do is at each step, I am giving you a pseudocode. At each step, sample a bunch of, let us say, some k of data points uniformly at random from the set of all data points. What does this mean? This means that you might have a billion data points to begin with. Now, what we are going to do is let us say our k is some 100. Now, we are going to uniformly sample 100 data points from this billion data points. Now, that can be efficiently done because you are just trying to get uniformly 100 indices from the indices from 1 to billion, which can be done very quickly. And then once you have these 100 indices, you can go and fetch these 100 data points if you have stored your data points in a reasonably good way, right? So that's not a big issue. Now, what you do in the next step is something interesting. You now don't have billion data points at your hand, you only have 100 data points. Now, you pretend as if this sample is the entire data set, right. So, is the entire data set, and you take a gradient step with respect to this sample, right. So, with respect to it. So, which means our gradient at the tth step is going to look like the following: 2 times not x transpose, it is going to be x tilde transpose w t minus x tilde y tilde. Now, what is x tilde? X tilde is just the just a bunch of data points that we sampled in this round, right. So, it is not a n cross d matrix anymore, it is just a 100 cross d matrix. It is not a billion cross d, it is just 100 cross d, because we are only sampling 100 data points. Now, what you are doing essentially is that you are pretending that in this step we only have 100 data points to look at, and we will take a gradient step with respect to only these 100 data points, as if this was our data set, and as if we are trying to minimize the squared error only with respect to this data set at this point. So, you take a gradient step that works only well for this data set, right. So, of course, this is manageable. Because you have x tilde which is in d cross k, right. So, where k is small, this k is the number of sampled points, that is it, that is the algorithm, right. So, n. So, this is the stochastic gradient descent algorithm. You start, you run this for t rounds. Note that at every round you are sampling k points, which means these k points are not the same at every round. That is the most important thing, right. Every round you get a different sample, though uniformly distributed from the set of all points, and then you are moving in the gradient direction along with respect to this sample that you have got at this round. Now, you can argue that this sample and the gradient that comes out of the sample is a noisy gradient, right. So, you had to compute the original gradient, but because you are doing this uniform sampling, you somehow have a noisy version of the original gradient and you are moving in a noisy direction, right. So, the question is, well, we are moving in noisy directions, all right, but then over time somehow does this noise kind of cancel out, and then are we overall making progress towards the original, W star that gradient descent would make progress towards. The surprising and the good news is that the answer to this question is yes, right. So, with a single small caveat that here in gradient descent, typically you do this, you start with some W naught, you move in the gradient direction to W1, W2 dot dot dot, W capital T, and after the end of T rounds, that W capital T is what you would output. Now, because here at every round there is a chance that you might get a noisy gradient and you might get an unlucky direction to move, just taking the last W capital T may not necessarily be a good idea, because you might have gotten a very unlucky sample in the last round and you might move in some arbitrary direction which is taking you away from the minimizer. So, instead what you do is, after T rounds, you typically use Wt given by stochastic gradient descent algorithm as just the average of all the W's that you have seen so far, Wt, right. So, this is one way to as opposed to the standard Wt that you would have used in as in standard gradient descent, right. So, instead of using Wt, now you are going to use the average of all the W's that you have seen so far. Now, what can we guarantee about this stochastic gradient descent's output W capital T is that you can guarantee this is guaranteed to converge to optima, which is W star with high probability. Of course, because there is a notion of randomness involved in picking the data points, there is a noisy gradient involved, we have to deal with probabilities here, but what is the guarantee that one can show is that you can converge to what you want, the W star, with very high chance, right, which is a good thing. Now, what you have done is you have kind of gotten away both the problems of D and N by first switching to gradient descent and then by switching to the stochastic version of it, and this works so well in practice, right. So, this K is what is called as a batch size. Now, depending on how much computation you can deal with, you can increase K or decrease K, right. So, the guarantee works independent of what the batch size is. Of course, the batch size will determine how many more rounds that you may want than standard gradient descent, because the smaller the batch size, slightly more number of rounds that you may have to run your algorithm for to get to the minimizer. Nevertheless, this is an extra computation which is much more manageable than computing XX transpose, which might be computationally very expensive, especially if n is too large. So, this algorithm is called as stochastic gradient descent, and this is what I wanted to discuss in brief about the computational considerations of an algorithm such as linear regression. Okay. So, we'll ask and answer a couple of more questions about linear regression, and the next topic that we would like to talk about is why linear regression, right. So, why did we choose linear regression, and why can't we have a more general, or maybe a not necessarily a linear relation between the features that explains the output variable y. What if, for instance, if it is a quadratic relation or something like that. So, that will take us into what is called as kernel regression, like how we did a kernel PCA. Now we are going to look at a kernelized version of linear regression, which is very similar. So we'll try to understand the kernel regression next.